Yeah, I hope the screen is visible. Yeah, okay. So today we will be discussing about something called a stellar evolution. This is just an artistic depiction of how the life of our sun will change eventually, starting from somewhere over here and becoming so big, 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 and finally become what you are seeing on the right side, that beautiful thing. Uh, Let's issue here. Okay. Yeah. So anyway, let's continue. Uh, just a second. Could you please wait for just 1 or 2 minutes? I'm right. Current now I am from my PC, but some issue with my PC, I think. So I will change to my laptop soon, just in a moment. So please, I'm sorry for the inconvenience caused. Just wait for a moment.
Good evening, everyone. Please wait for 2 minutes. Sharat sir is facing some technical issues. He will join us soon. Okay.
Hello. Yeah. Okay. So I hope I am audible right now. Well, yeah. Okay. So now my pen is also working. Yeah. So sorry for the delay. So we lost some 7 to 8 minutes, but anyway, we will continue till 7:10. So don't worry about the timing. So today we will be, let's continue. Let me share the screen. Okay, so this is the topic that we are going to discuss today. So yesterday we discussed about the sun and the structure of sun and how is the energy being generated inside sun. And now the problem is that is this energy for a is it infinite energy or it will happen forever till the end of the universe maybe uh, uh, is there any such supply, like is that energy is infinitely available? But as you know that any energy, it is not infinitely available. Even if it is nuclear energy, we say that it can go up to some billion years, it's fine. As we discussed yesterday, sun even can go for last up to some already went for some 5 billion years, and the remaining 5 billion years also it can run. So every star has a lifetime like that. It has to born from something and it has some middle age or its young ages, then it's reaches its old age and die. So this thing happened for stars as well. So let's see how this happens for stars, or what are the different steps that is happening in between the stellar evolution, or what is exactly happening throughout this thing. And that exact thing, that path through which the sun and all this sun or the other stars are going is called the stellar evolution, or the process of going from one end to the other of that is called the stellar evolution. Okay, so let's see how that star get evolved and how that lifetime is going. So before that, we have to start from the beginning. That means the star has to born from something, and that something is actually from the molecular clouds. Okay, so we call it as molecular clouds, and it looks like cloud as well. Okay, so you can see here, this is a famous nebula, and this molecular clouds are known as nebula. Okay, they are called nebula, and this is one of the famous nebula called uh, pillars of creation, or eagle head nebula. It is called the eagle head. It looks like an eagle head, or most famously this photograph particularly is known as the pillars of creation. Why it is called the pillars of creation? Yeah, here inside this nebula, lot of star creations are being happening. So that is why it is called the pillars of creation. And this is not the only nebula that we have. There are many number of nebulas are there, even inside our galaxy and outside our galaxy, in other galaxies as well. And nebulas, even though looks like a cloud, actually it looks like a dense cloud or something like that. But one thing that you have to notice, okay, the number of particles inside that nebula, okay, that means if you take 1 meter cube, that means if you take a box, consider a box inside that nebula with 1 meter side, 1 meter width, 1 meter, a square box of side 1 meter. Okay, can imagine one. Okay, so if you consider something like this, it will be so tiny anyway in this scale. But anyway, if you consider a box full of this material, then it will consist of 10 raised to 5 particles. So yesterday we discussed what is the meaning of this 10 raised to 5, that is 1 followed by 5 zeros. So that many number of particles will be there. So we feel that it is actually 100,000 particles. It's a huge number. But when we compare with the normal air we breathe, the air that you are right now breathing, it actually, even that itself actually consists of 10 raised to 25 particles. See, that is 1 followed by 25 zeros. That many particles are there in the air we breathe. So when you compare, even though it looks like a dense cloud or something, it only consists of a very few number of particles. So that is one thing. So when we see this picture, we think that it is so dense, but it is not even comparable to the thickness of our air. Okay, but then why we are seeing it like this? Because it is so giant. It is not just a small thing. Usually its size is across some thousands of light years. Okay, you can see the size from this side to this side is of something like a thousands of light years across. It is so vast actually. It is not just a small thing. That is why we are seeing it as some thick cloud because of the size. And see, even with that number of particle and because of this huge size, the mass, okay, see the total mass of this nebula, or we call it as a molecular cloud, is actually around 3 million solar masses. Okay, 3 million solar mass means it is 3 million times the mass of sun. Okay, so just the mass of sun is of 1 followed by some 26 zeros. Okay, and its 3 million times is the mass of this molecular clouds. And this molecular cloud has some more cold dense regions are there. Even you consider this, there are some cold dense regions are there, and they are called clumps. Okay, and that clumps, okay, within that clumps, even denser small regions are called cores, or they are called the embryo of stars. Okay, so that is where the stars are being formed. So inside that normal molecular cloud, there will be clumps of material. Clumps means, you can, by the word meaning itself, something that is close together, that is clumps. Okay, so it is so it's clumps called the clumps, and within that clumps there is core, and they are called the embryos of stars. And within that embryos, a star starts to uh, uh, starts its life. Okay, so before that it is something like a cloud. Okay, it's a thick cloud, and within that embryo it is smaller in size. But what happens is that when there is some other external influence, like another shock wave or something, sometimes this within this cloud start to what to say, they start to collapse together, or assume that one particle is here, one particle is here, one is here, one is here, one is here. This was the initial state. Initially this our cloud was like this. Okay, but suddenly, because of some external reason, the four of them came together. Okay, so four of them came together means they are now so close. Okay, so they comes together. So when something comes together, its thickness increases or its density increases. So when the density increases, we know that it can pull more material. So denser means it can get or attract more nearby particles. So it will attract more nearby particles. Okay, so because of its increased gravity or that gravitational force, it can attract more nearby. So it will come again. So all this what you are seeing nearby will comes together. So that becomes something like so close by. So it is increasing in size. You can see it is size is not increasing anyway. They are actually collapsing together. Okay, so gravity pulls the particles nearby, all the nearby particles, and there are many things will happen. One thing, as the things comes together, okay, as all these particles comes together, the central core, the central part of this starts to heat up. The temperature will increase. So it will come together to form like a ball or something, and it starts to, its center core starts to heats up. And along with that, there will be a disk of material swirling around that. Okay, and from that swirling material, or that round orbiting material, that will be fed to the center core. Okay, and it is keep on happening, and the more matter will come, the temperature will increase. More matter will come, the temperature will come, and it keeps on rotating as well. Okay, now the temperature is again and again is increasing, and because of that temperature, okay, what temperature it is? The temperature, because the particles or the materials are collapsing. Because of that collapse, there is heating up. Because of that heating up, this ball of gas starts to glow. Okay, it starts to glow. It is not yet a star. Okay, because of the temperature, it starts to glow, and it is called a protostar. Okay, and you have to notice something. In a protostar state, there is no fusion. What is fusion? Yesterday we discussed. That is, for a star, the energy generation or the fuel of that star is actually not anything like the petrol or gasoline or anything. It is basically the nuclear fusion. Hydrogen comes together, fusing or comes together and forms helium. That is called the fusion. But in a protostar, yet no fusion has started. Okay, so cores heat up, and it gives a glow because of its heat or the internal heat. That's all. There is no. It is not glowing like a something called. It is not glowing like a star. It is a faint glow when compared with the star's original brightness, but it is the just before stage. And we can say that this is the beginning of the star. Okay, so from a molecular cloud or nebula, a star starts to form like the matter is collapsing together, and it becomes a ball, and it heats up, and it has a certain temperature that becomes a protostar. Now, the next step is actually the birth of the star. So for the birth of the star, there should be something happening. That four hydrogen should come together and form that helium that we discussed. Or simply, the fusion has to happen. So for that fusion to happen, there we need a high temperature at the core. Okay, so at the birth of the star, okay, so at the core, the temperature, you just leave all these things in the left side, okay, because you can read it later. I will explain it anyway here. Okay, but not all of them, because this is not just for you. This is actually applies to for seniors also. But anyway, even though it is a senior material, it is better you can at least read through them, even though you couldn't understand. At least when you go to some higher classes and all, it will be helpful. That is why I am giving you this slide. Okay. Okay. So you can see that at the core, okay, the temperature is rising, and at that center, so the problem with the fusion is that, that for fusion to happen, okay, it won't happen normally. Okay, you cannot take four hydrogen and keep it together, let it become helium. It won't happen. It needs a very high temperature. So when the protostar heats up and its core temperature becomes enough for the fusion to happen, then suddenly there is a burst of energy outward, or the nuclear fusion starts. So we can say that the star get ignited. Okay, so when the star get ignited, okay, it happens around some 10 million Kelvin. So at least 10 million Kelvin is needed, not at the surface, at the core, for a star to ignite its hydrogen fusion. Okay, so the fusion of hydrogen will happen only at this very high temperature. Okay, now that's okay. No doubt in that. Now it will happen, but there is a problem. So yesterday I told you that it is something like a bomb, huge amount of energy surging outward at momentarily. Okay, so every second, a very high amount of energy is going out, means it is something like a bomb. Okay, it's like an explosion. But a star doesn't explode. Okay, even if you take the case of sun, you know that the sun is not exploding. Why it isn't exploding? Yeah, the reason behind that is gravity. So we know that there is an outward, this red color, you can imagine it as the outward pressure, because of high temperature and energy and light is happening from the center, and that center is pushing the star outward, or trying to explode the star. But the star is not just like a bomb actually, because the star is so massive, so that there is another opposite force is there. You can see that there is another force that is happening inward, which is the gravity. So the star has its own gravity, like Earth also has its own gravity. It is pulling everything inward. Similarly, the Earth is also pulling everything inward. Okay, from all sides it is pulling inward. Similarly, the star also pulls everything inward. Okay, so that pulling due to gravity is there. So you can see that there is one force outward, that is the pressure due to this high energy. Then there is another force that is coming inward, that is the gravity. So this is gravity and this is the pressure. So this pressure and gravity are in a balance, or they are equal. Okay, when they are equal, it won't explode. Okay, so if the pressure is more than the gravity, it will expand, and if gravity is more, the star will collapse. Happen. But usually when you see a star after its birth, it is in a balance. The gravity and pressure are equal and they will cancel. So it is in a balance, or in terms of science, we call it as equilibrium. Equilibrium means it is equal. Two or three things, everything is equal and cancelling out each other. Then it is called equilibrium. And this equilibrium in a star is called hydrostatic equilibrium. Okay, so it is called hydrostatic equilibrium, the equilibrium inside a star. When there is a hydrostatic equilibrium, the star will stay like this. Nothing will happen for the star. It is stable there. Okay, but when something happens for the star, something like if it runs out of fuel, then what will happen? The outward pressure will decrease, so that gravity dominates. Okay, and sometimes imagine that the outward pressure, the burning rate increases, then what will happen? The pressure will increase, so the star will expand. So that is how the life of a star goes on. It depends on what is happening at the center, whether there is enough energy. Yeah, if it is enough energy outflow, it will be in a balance. If there is not enough energy outward, then the gravity will try to collapse the star. And if there is more energy at the center, the star will expand. So based on this thing, we can actually explain the life of the star. So this is actually the birth of a star. Okay. Now there are some mass criteria. Okay, so anything cannot become a star. Any gas, anything, every protostar like this won't become a star. Okay, so protostar can form anywhere. That's not a problem. But any protostar cannot become a star. There is a mass limit. Okay, and it is first is called the Jeans mass. Okay, it's called Jeans mass. That is the minimum mass required for a gas cloud to collapse under its own gravity from a protostar. Okay, if a cloud of mass less than the Jeans mass, it will not collapse. Instead, it will disperse due to thermal pressure. So there are, you can imagine, there are some stars which doesn't or there are some protostar which doesn't have enough mass, they cannot become a star. But if the protostar has enough mass so that it can collapse, okay, so every gas cloud cannot become a protostar. The gas cloud which can become a protostar has a certain mass. Okay, and that is the case. And there is one more thing. Even though if there is, the Jeans mass determines whether a gas cloud can become a protostar or not. Okay, that is the Jeans mass. Now there is a hydrogen burning limit. Now the protostar is formed because assume that it has enough Jeans mass and the hydrogen burning and the protostar has been formed. And now the protostar need to sustain hydrogen fusion in its core. Okay, so that means it has to happen the hydrogen fusion, and only if its mass is at least 0.08 times the mass of sun, or in other way, its mass should be 80 times the mass of Jupiter. So what it has to do with Jupiter? It has nothing to do with Jupiter. We are saying the mass of Jupiter just for a comparison. So if the protostar has a mass equal to or more than 80 times the mass of Jupiter, then it becomes a star. Okay, just leave the name main sequence. I will explain it later. So anyway, then it can become a star. And there are some other star which becomes protostar, but it has mass less than 80 times the mass of Jupiter, and they are called brown dwarf stars. So what is the problem? It was a protostar, okay, but its mass is less than 80 mass of Jupiter's. So what happened? Yeah, it cannot, it wanted to become a star, but it couldn't become a star because it doesn't have enough mass. Okay, so that is called brown dwarf. Those stars, those failed protostars are called brown dwarf. Okay, now there is another thing. So there is a minimum limit for a star mass. That means a star should at least weigh 80 times the mass of Jupiter. That is the minimum mass a star needed. Is there an upper limit for a star? Yes, there is an upper limit for a star. That is called the Eddington limit. So according to this Eddington limit, we cannot have a star that is more massive than this range. Okay, so we cannot have a 200 times solar mass star. Okay, the star should be within the limit of 100 times to 150 times solar mass. You cannot have a star more massive than that. So that is called the upper limit of a star mass is defined by Eddington limit. So what is Jeans mass? Jeans mass defines whether a gas cloud can become a star, protostar or not. And what is hydrogen burning limit? It defines whether a protostar can become a star or whether it becomes a failed brown dwarf. And what is Eddington limit? It is the upper limit of the mass of a star. Okay. Now let's go ahead. Now what is happened? The next level of star is called. Now assume that it does have the enough mass so that the next level can happen. So the next level is the hydrogen burning. So the nuclear fusion starts. So what is the nuclear fusion? So the happening nuclear fusion is at the center. Okay, it happens only at the core, nothing else. Yesterday also we discussed that even in the case of sun as well, sun is a star. In the case of sun, the what is called the burning, the hydrogen to helium conversion and the energy generation is happening only at the core. Okay, it will happen only at the core. Okay, so what is a main sequence star? In the case of a main sequence star, it is the most stable phase of its life, and it is the longest aspect. Okay, so we can say that it has different parts of life. Something like you were something like a baby for some 2 to 3 years, and your education period may be something from 4 years to maybe some 18 to 20 years or 21 years. So that's a long period. Like that, the star's life is also, we can define, distribute into different classes, or we can say that it is different phases. And out of that phase, the main sequence star is the longest and most stable phase of a star's life. Okay, and when it is there is a reason for calling it as a main sequence that I will explain later when if I discuss that something. Okay, let's wait for that. But anyway, that is called a main sequence. What is the speciality of main sequence? Yeah, the hydrogen at the core, the hydrogen is being converted into helium. Okay, then around that there will be a radiative zone, then there is a convective zone. It is similar structure that of a sun. So that why? Because sun is now in its main sequence stage. Okay, so if you want to get an example of a main sequence star, the best example or the easiest example is actually the sun. So sun is in the main sequence. It is burning hydrogen at its center and it is being converted into helium. This is going on and on. But there is a problem. So this is the main sequence stage. Now what will happen? So the hydrogen is being converted into helium and the remaining part here all mostly it is actually hydrogen. Now imagine that what is our fuel? It is hydrogen. And what is the product after this burning, or we can say what is the ash? That is helium. But the problem is that after some time, the hydrogen, we get out of fuel, or we get out of hydrogen because we won't have enough hydrogen after certain years. Okay, for example, okay, before going to that, you can see that these are all the life of main sequence. You can see that if the star is so massive, like the 40 times the solar mass, then its lifetime is, the main sequence lifetime is 1 million. And if it is 0.4 times the solar mass, it is 200 billion. You can see an interesting thing. If the star is so massive, then its life expectancy is less. Okay. You can see 10 million. Okay. Then it comes million, billion, and 200 billion. See that? 0.4 mass, 0.4 times the solar mass will last for 200 billion years. Okay. So that is about it. So the more massive stars can live less, and less massive star lives longer in their main sequence thing. Okay. So that is about the lifetime of each of them. Now let's go. Then what happens when it runs out of fuel? Okay. When it runs out of fuel, that means in the core or at the center, all the hydrogen is being converted into helium. So just imagine something like, just leave this image and all. Just imagine. So the hydrogen is being converted into helium. Now there is no hydrogen remaining. So the hydrogen is completely converted into helium. That means now there is no outward energy flow. Okay, that means the fusion at the center stops. So that stops means there is no outward pressure, and we learned in the first couple of slides that there is two forces are in balance. There is an outward pressure due to the energy, and there is an inward gravity. The gravity is still there, but there is no outward force. What will happen? There is nothing to push the star outwards. There is only an inward push. So because of that inward push, okay, especially the dense core compresses or collapse. The core will collapse. Collapse in the sense it is not completely collapsing, it shrinks basically. It is better to say that it shrinks. Okay. So the core will contract or shrinks for some time, and the outside part will also contract. And during that contraction, again the temperature will rise, and the outside, the helium core remains like that. And since the temperature again risen, that is raised, the shell, that is, this is helium, that is completely, that is the ash you can imagine, and the a shell around the hydrogen around that starts to burn. Okay, so a shell of hydrogen around that starts to burn. So now what is the structure of that star? Yeah, the helium is at the center. It is not burning at all. It is helium, and there is a hydrogen burning at the center. Okay. Now at this stage, something else happened. Interesting. So due to this hydrogen burning outside, the star starts to expand. Okay. So the core will contract at the same time because of the high energy outflow from here. So this thing, the hydrogen burning shell the outside hydrogen. So this is the helium, this is the hydrogen burning, this is plain hydrogen. It is not burning. That shell starts, the outside layer of the next outside layer of star starts to expand. And expand means the star increase in its size. Okay. So it becomes, since its size is becoming so big, it becomes more brighter, but its temperature is less. Okay, the temperature will, the star will, surface of the star will cool down, at the same time its size will increase, and that phase of a star is called a red giant. Why it is called a red giant? It is giant because it is expanded and it is red in color. Why? The cool stars appear in red and the hot star appear in blue. Okay, so it is not what you think normally. So in the case of stars, especially, the hotter stars are bluish in color and the colder star are reddish in color. So the stars cool down and it expands. So it get a red color and it expands because and it becomes a giant star. So it is called a red giant. So now after this red giant phase, okay, the core again compresses because there is nothing in, no burning is happening at the core. So there will be, again the core will shrink, and when the core will shrinks, again the core temperature will increase. So now another thing will happen. Okay, so at that moment, at the core, what was there? Helium was there. It was staying there. It is not burning or anything. It was there. Okay, staying like that. And what was in the outside shell? The hydrogen was only doing the energy generation duty. Helium was staying like that. Okay, now the helium starts to burn. Okay, now what is happening? The helium burning will happen. So now see the structure of the star, the center, that is, so as yesterday we learned only hydrogen can become helium. Okay, but here again that helium again becomes another element or another nucleus. Okay, something like oxygen or carbon. Okay, so the helium becomes carbon and oxygen at the core, and also energy generation. So that is the fusion of helium. So we can say that at the core helium fusion is happening, at the next outside shell hydrogen burning is happening, and next outside shell the hydrogen is there, nothing is happening. Okay, so that is the case of the star. And when the core starts to burn helium, it is called a helium flash for low mass and a medium mass star. Okay, so that is about the next level. Now this keeps on happening in the sense that now there is helium is being converted into carbon and oxygen. Now after a certain time, at the center, okay, there won't be enough helium to burn. So when helium is not burning, again the fusion stops. Again it can expand. Okay, and it keeps on repeating. But in the case of sun, okay, that we will explain later when we discuss about the giant stars. But in the case of sun, this will go ahead and it will completely become carbon and oxygen, mostly carbon. Okay, and then another interesting thing about this red giant phase is that you can see that when the sun becomes its red giant after some 12 billion years, okay, at the age of 12 billion years, that means some now some 7 to 8 billion years more. After some 7 to 8 billion years, you see the sun will expand its size and it becomes near the earth's orbit. You see, this earth is actually so near to the sun at that time. Okay, after some 6 to 7 billion years after, this will be the case of our sun. So sun will expand into a giant phase, or we call it as the red giant phase of sun. Okay, this red giant has some specialities. Its radius will increase to 100 to 1000 times. Now here you can see some other red giants. It is basically not just giants. There are some super giant stars, Betelgeuse and Taurus, Aldebaran, and I don't know whether you can see the sun. Actually, the sun is here, a tiny dot. So that is the size of a giant stars when compared with the usual. Okay, so the surface temperature drops, that we already discussed. Then the radius, the size will increase. Then the luminosity also increase. The energy generation will also increase because of this burning. Okay. Now in the next stage, okay, so this is the final stage of sun. Okay, what will happen? So the helium is there. Okay, so the center becomes carbon and oxygen, and in the next layer helium is fusing, and in the next layer there is some helium core is there. Then hydrogen shell is fusing. Then the hydrogen envelope is here. So it may be a bit complicated for you. You can imagine it's something like an onion. Okay, there are different layers, and each of the layer different content or different process are going on. So at the center, carbon and oxygen is there, and next outside the helium fusion is happening. Then next outside helium core. That means there is no fusion in this layer. Okay, so wherever there is fusion in that layers, only the energy generation is happening. All other state you can see core, and envelope. These are all not generating energy. Okay, so this is what will happen for sun. And at that time, because of the burning is happening here and here, okay, that is hydrogen shell is fusing, so the stars even starts to expand more and more because of the high wind. So something we learned yesterday called a solar wind. So there are stellar wind happening from these stars, and the star will starts to expand, and okay, and it ejects out its outer layers. So the star will starts to eject its outer layers and expand because of the strong stellar winds. Okay, so the core again, that remaining core, that is the especially the carbon core will stay like that. Nothing will happen for carbon core, but the remaining part will expand. And now there is one more thing. This carbon core is not burning anything. So it is not burning, but because of the high temperature, it emits some ultraviolet radiation, and due to which the surrounding ejected material glows like this. Now you can see, and that final stage is called a planetary nebula. So you can see a planetary nebula here. So I will explain here. So what is this? What you are seeing around this, something like a, maybe something like an oasis or something. So this round, this material is actually the material that ejected from that star. Okay. For low mass stars, something like the sun-like stars, this will happen. So it is ejecting out material, and that ejected material will form something like a big ring around it. And at the center, that core will remain there, and that core is of carbon for the stars, something like the sun. For sun-like stars, this core will be of carbon, and that carbon core is called white dwarf. Okay. There is reason for calling it a white dwarf because, yeah, that core is basically, its size is something around 1.1, not the size, its size is around the size of Earth, and at the same time its mass is something about the mass of a sun. Okay, something nearly or less than the mass of sun. So it is so dense material, that is the white dwarf. So if the and if the if this white dwarf can only exist only if its mass is less than the Chandrasekhar limit, which is called the 1.4 times the solar mass. That means if the white dwarf is more than 1.4 times the solar mass, it cannot stay like that. Okay, there is something else will happen for the white dwarf. If it is not, or it will collapse again. But if the mass is less than 1.4 times the solar mass, then it can become a stable white dwarf. It stay there for a long time, extremely hot. It is not because of the energy generation, it is because the compression of gravity, and there is no fusion at all, and the white dwarf slowly cools and fades over billions of years. Okay, and after trillions of years, the white dwarf will cool to become a black dwarf. But this is, we are not sure, because it takes trillions of years to become a star to become, or a white dwarf to become a black dwarf. It takes trillions of years, but we couldn't observe any because the universe is only just some 13 billion years old. So we cannot see something that happens after some trillions of years. And you can see an interesting fact about the white dwarf. A teaspoon of white dwarf, just go and take a teaspoonful of white dwarf matter, then it will weigh 9,000 kg. So that much densely packed, that much thick is the white dwarf is. Now what you are seeing here is not a white dwarf. So you may think that this is a white dwarf. No, this is the star called Sirius. Okay, and now I am calling it as Sirius A. Why? There is a Sirius B. Can you see this tiny star here? This is called the Sirius B. And the Sirius B is actually a real white dwarf star. Okay, so that is about the end of sun-like star. So what will, just we can just summarize it. Just see, initially that happen, what will happen? Yeah, the star will burn by fusing the hydrogen fusion. Then after that, the hydrogen is being converted into helium at the center, and after some time the helium is completely burned, hydrogen is completely burned, and there is not enough hydrogen to burn. So in the next outside shell, it starts to burn, hydrogen burning will happen, the helium will stay like that. Then after some time, after some contraction, the helium starts to burn at the center and becoming carbon. Then there is a hydrogen burning shell outside, and something like that will happen. And eventually, what will happen? The star will get a structure like this with an inert core, or in the sense that there is a non-burning core of carbon and oxygen will be there. Then helium fusion in the next outside shell, and because of the helium fusion and hydrogen fusion in the outside shell, the star will have a heavy solar wind, and because of that, the outer layer will be ejected to the vastness of space, and it finally become something like this, and it is called a planetary nebula. Okay, and the center core, that the carbon and oxygen core, will become will be known as a white dwarf star. Okay, so that's about it. Okay, now let's go evolution of, so this is the end stage of sun-like star. Why it is called a sun-like star? This will happen for sun and the stars whose mass is less than 8 solar mass. Okay, if the star's mass is 8 times less than 8 times the solar mass, then its life will be something like this, or its life story goes like this. But in the case of stars which are, okay, high mass star, that means if it is mass, it is more massive than the sun, 8 times more massive than sun. That is something like if it is some 10 solar mass, or if a star has a mass of some 20 times the mass of sun, then its life is bit different. Okay, in that case, finally there will be a series of energy generation will happen, and finally its structure becomes something like this. You just see there is a silicon sulfur fusion here, then magnesium neon fusion here, carbon oxygen fusion, helium fusion, hydrogen fusion. So there are different kind of fusion will happen, and at the core there will be only iron. Okay, so we may think that why don't iron fusion may happen, but iron fusion doesn't happen because iron nucleus is so stable that we cannot make it fuse to form another element. So it becomes iron core and the fusion stops there. So when the iron fusion stops at the core, if there is no iron fusion, that means entire core becomes iron. Suddenly everything at the core stops, and eventually that iron core will collapse. So that iron core will starts to collapse. Okay, and that collapse will cause an explosion. So it is actually initially it is happening a collapse, and after that, because of that collapse, the star becomes an explosion. Okay, and that most energetic explosion is called a supernova explosion. Anyway, what you are seeing on the right side is not a supernova explosion. This is what remains after, this is the remnant of a supernova explosion. And supernova explosion has many things to do with even with our life, actually, that I will tell you later. So you can see that the core will collapse, and because of that, the outer layers will be ejected at high velocity, and it will become something like this. And these kind of supernovas are called a type 2 supernova. Type 1 we saw last class. Okay, so and one more important thing is that you can see that there are something happening. So hydrogen, okay, and hydrogen become helium inside a star, helium become carbon and oxygen inside a star, and this carbon and oxygen become magnesium, neon, oxygen, etc. inside a star, and it becomes silicon inside a star, sulfur inside a star, iron inside a star. So what is its importance? So all these kind of elements, okay, initially when the universe was formed, there was only hydrogen and some amount of helium, that's all. Okay, but we know that in our life, in our periodic table, there are many kinds of elements. How they are all formed? Are they formed inside a chemistry lab? No, never, not at all. So all these elements up to iron is actually cooked up inside a star. And what about the remaining? There are some calcium, then uranium, maybe beyond that, there are many elements are there. So how those elements are formed? Okay, chlorine is there, then silicon is there. So how we got all other remaining elements? Okay, apart from this element, these are all cooked inside the star, and the remaining stars elements are cooked during that supernova. So during a supernova explosion, all the remaining elements, all the naturally occurring elements in the periodic table or in the maybe what we learn in your science, all those elements like the calcium, magnesium, uranium, neptunium, there are many, okay, a lot of elements, some 100 elements are there, almost, even more than that. most of them, all of the natural elements are actually cooked during or made during the explosion of star. So that is why we have all these elements in the universe. So otherwise, if there was no massive stars, so that is, even though we say that the life of a massive star is less, something like the just millions of years, but when you take a low mass star, it is billions of years. But even though they live for a small time, okay, they makes all the necessary thing that we need. So the massive peoples are not that bad. Okay, so being massive is actually good in the case of star. That is why we have all this elements in the universe. So what about the remaining core? So there was an iron core. Okay, so that iron core is there, and that iron core becomes, okay, if the iron core, so now this is some more interesting fact about supernova. So energy released is approximately, so it is not about the star, it is the supernova. Supernova usually happens some over some days actually. It takes some maybe days or months or weeks actually. Okay, the duration of a supernova is just weeks, not years or millions or not even years. It is just weeks of thing. It happens within a week, and the energy released is 10 to the power 24 joules. That is 1 followed by 44 zeros. And see, it is 10 to the power 9 times. That is 10. That means a billion times more than the sun's energy over its entire lifetime. So if you give an entire lifetime for sun and all the energy combined, even that is actually not even comparable with the energy of supernova. Okay, so the entire energy that is sent by the sun over its entire life, it's 10 raised to 9 or its billion times is actually the energy emitted by a supernova within a week of time. Okay, and you can see that that supernova can outshine the entire galaxy for a brief period. So it's so bright, okay, and it is billion times brighter than sun. Okay, that's at that time. Okay, it is not for a long period, and its temperature of the core become 10 billion Kelvin. But at the same time, the core temperature of sun is just million Kelvin. See, that is 10 billion Kelvin is the temperature of the supernova. Okay, and also supernova emits its material at a speed of 10,000 to 30,000 kilometer per second speed. Okay, but at the same time, yesterday we learned solar wind is about just 400 to 800 kilometer only. And you can see this is a photograph of a supernova. It is not the remnant, but it is a supernova. You can see it's like a star. See, a dot is there. So that dot is actually supernova. I got an opportunity to observe something like this through a telescope as well. But you may think that I can see a magnificent explosion or anything, but we cannot see it like that. But when we look at a supernova through a telescope, you will see it as a bright star. Okay, but you just imagine when you're observing usually a galaxy through a telescope, you will see it as just a faint cloud. But out of that is the entire galaxy, the case of entire, we cannot distinguish any of the star. But suddenly when there is a supernova, that particular supernova is, we can see like a star. That means it is that bright, even brighter than the that entire galaxy. So that is supernova. Now, if that supernova, in that supernova, there is a core, that iron core was there. Okay, if that iron core, the remaining iron core is between 1.4 and 3 solar masses. Okay, and it becomes, or it stays like a neutron star. Okay, and all the iron will be compressed and it completely becomes made of neutron, and that is called a neutron star. So that, what is the case for that? If the mass of the iron core is 1.4 or 3, between 1.4 and 3 times the solar mass, then it stays like a neutron star. And neutron star has a speciality, it is very high, it has a very high magnetic field, maybe more than some million times magnetic field of the sun. So it is so highly magnetic, and at the same time they are incredibly small, in the sense that its size is some 10 to 20 kilometer only. 10 to 20 kilometer means it's the size of an average, a small city will have a size of 20 kilometer. So, and what is the mass? Something like the 3 times the solar mass has been into a very small region like this. So it weighs some billion tons. If you take a teaspoon of material from the neutron star, it will weigh something billions of tons. Okay, and it also emit a kind of a beam of light from this poles, and we can see it will be rotating as well, and we can see it as a pulse. Okay, they are called a pulsars. And now another interesting thing that comes out of the neutron star is that if the neutron star is more massive, that means if it is more massive than the 3 solar mass, or 3 times it is 3 times, yeah, if it is mass is something around 5 solar mass, that means it is greater than 3 solar masses, then it will again compress and it will form something called a black hole. Okay, so that is the final case, that it is gravitationally collapsed and it becomes a black hole, where what is the speciality? Already for all this material, they are so compressed material. When you take something, okay, imagine anything, okay, and if you compress it, okay, compress it into smaller and smaller, its gravity becomes more and more and more. Okay, so now we are actually compressing something more than 3 times the sun's mass, and if you are compressing into even less than a point, which is actually 10 to 20 kilometer, even less than that, then it becomes highly dense so that nothing can escape from it. Even light cannot escape from that material, and that is called a black hole. So that is about it. And this is the photograph of the not of the black hole. It is just outside the black hole, and the black hole will come inside. Okay, it is taken by the Event Horizon telescopes. Okay, so that's about it. And if we brief it together, okay, all these formations, you can see that the nebula was there. We can categorize it into two: for low mass or the medium mass star, including sun. Nebula, the main sequence, that is hydrogen burning, then red giant, and finally it expands and form planetary nebula. And what remains, planetary nebula will be there, and at the center white dwarf will be there. So this is the simple path. You just understand this diagram well. That is more than enough for you junior students. This is enough. And now what about the high mass star? Yeah, from nebula there is high mass star, main sequence, and they become red giant, but it is not just simple red giant. We call it as red supergiant, and those red supergiant explode, and if it is high mass star, it becomes a neutron star. If it is very high mass star, it becomes a black hole. Okay, so these are the end results of a star. Okay, if a star dies, it becomes either a white dwarf, either a neutron star, or a black hole, and it depends on its mass. Okay, so what defines its end stage is its initial mass, what it acquired at the beginning, what was its beginning, or how much massive it was at the birth time. That defines the end of a star. So according to that, our sun will not become a supernova, it becomes a planetary nebula and a white dwarf star. So, or finally, we can say that our sun will end as a white dwarf. So that's about it. Now, one more thing, just leave. This is just the brief of what I have explained. Just you can read it later. But I have said something called a main sequence. So main sequence, don't worry about this graph and anything. I will like try to explain that. So scientists did something interesting. That is something like they tried to arrange stars in a graph. Okay, so a graph means here you can see that the temperature is decreasing in this direction and its energy output in this direction. And here they try to put all the stars. They will identify a star and find its energy output and its temperature, and they find a position here. And for all the stars, they found a position for each stars they observed. And when they observed, the most of the stars they observed comes into a sequence like this. Okay, something. Then there is some other, if you look, red supergiants becomes a group here, simple red giants becomes here, blue giants comes here, white dwarf has had a position like this. So they haven't expected this, but when they arranged it like this, they got most of the stars are here. That is called the that becomes something like a sequence, and that is why the name the main sequence, or this is the most important or the main part in the case of a HR diagram, and it is the most populated region as well. And we will you will learn it in the higher sessions and all, maybe after if you appear for senior session and all, then you will learn about HR diagram and all, but just see this, that's all. Okay, it is not there in your syllabus as well. HR diagram is not there in your syllabus anyway, just shown, that's okay. So that is about the life cycle of star. Okay, now let us go to the chat, then I will come to you and ask the question. So what makes the stellar nebula to collapse? So there is no need to put any more questions in the chat. Okay, after one or two questions from or some questions from the chat, I will ask you directly, don't worry. So the stellar nebula collapse because of some shock waves nearby. If something like if a gravitational collapse of a star, that means a supernova happens nearby, that supernova itself can cause the formation of another star. That is one example for the, or that is one of the causes for the collapse of a nebula. Okay, there is no need to put more questions in the chat. Okay. If light does not have mass, then how it gets attracted to black hole? Light doesn't have mass, but according to Einstein's theory of general relativity, even though the light doesn't have mass, it can be attracted. It can get attracted. Okay. Topics from preliminary will be in the intermediate exam. I think you can ask that clearly. Will the topics from preliminary level be in the intermediate exam? So you can ask, contact the EduMitra customer care for that. I think there isn't, but anyway, just clarify. Okay. So what are hypernovas? So hypernova says it is also a supernova, but if the star's mass is something around more than 30 times the solar mass, okay, then in that case, it will be even more giant explosion, even more energetic explosion. They are called hypernovas. What is neutrons made up of? Neutrons are basically, you imagine it as neutrons, that's all. It is actually made up of something called a quarks, but there is no need to learn about. So no need to put questions in the chat. I won't take that. I'm coming from the last to the first. So I will ask one by one. You just hand raise. Okay. So supernova is basically the blast of mass of a high mass star, right? Yes, exactly. Recording, I think, I don't know, you can contact the EduMitra customer care for that. Anyway, you will receive. Anyway, for the recording as well, you have to contact the EduMitra customer care. Looks like. So I haven't mentioned anything like it's brown dwarf. Okay. Which more massive white dwarf for okay. So which is more massive, white dwarf or brown dwarf? Obviously, white dwarf will be more massive. Can any star fuse iron? No star can fuse iron. It is because of the physics. Physics doesn't allow it to fuse. Okay, so the iron is the ultimate limit. Beyond that, there is no fusion happens. So will the hydrogen burn instead of helium in the cool star? So whatever be the star, the initial burning will happen for hydrogen. Then only helium. Then only the next. Then only the next. That sequence or that order should be followed. Why do stars with the higher mass have a longer lifespan? Oh, sorry, this is you misheard, I think. Actually, the lifespan of low mass star is higher than the high mass star. High mass star lives on shorter; it won't live longer. Okay, low mass star lives longer. So if the mass of a star becomes more than the Eddington limit, because of its energy, it will actually, because of the burning, it will go away. That means the star will wither away. We can something like that. Because of high solar wind or the stellar wind happening, because of the high energy, the star won't stay like that. How a protostar can emit infrared radiation. So anything that has heat, a temperature, it will emit infrared. For example, my body itself is emitting infrared right now because my body has a certain temperature. Okay. Now let me ask questions one by one. Okay. So first, Chakri, you can ask.
What if two black holes collide?
Yeah, what if when two black holes collide, it becomes a bigger black hole. It becomes a giant black hole. Okay, so that is the thing that happens when two. That is what is the output of a what is called a merger. It is called a merger of black holes. And during that merger, the output result or the final result is a bigger black hole. But also there is one more thing. During that, there will be a high energy emissions will be there. That is a very high energy gamma rays. If you remember the first class, that gamma rays is there. So high energy, they will be emitted. And there is another thing called a gravitational wave will be there. So these things can be. And that high energy emission of gamma rays are called gamma ray burst. Okay. Now next, Animesh Prakash. Okay, Animesh Prakash, you can ask.
Sir, I
Ah,
basically got three questions.
yeah,
How can protostars emit infrared radiations?
yeah. Anything that has a temperature or heat. Okay, so your body has a temperature. If you check with the thermometer, you can see how much degree it is or how much Fahrenheit it is. So anything that has a temperature that can emit infrared. Okay, so protostar are even high temperature, so it can emit light and it can emit temperature. So it is hot, but it is not that hot to become a star, but it's just before becoming a star. It is high in temperature, so it is so hot gas is there, so it can emit not only infrared, any light can be emitted from that.
Sir,
Ah,
my second question is, do black dwarfs do look like this?
not at all. We don't know how it looks like because we cannot see them.
Okay.
Yeah.
So, sir,
Ah.
finally, my third question is there anything bigger than a supergiant?
There are supergiant, hypergiants are there. That are all just naming convention. Hypergiants, or usually we don't say that in astronomy we say that it's supergiants. So it's not bigger than that.
Oh, I get it, sir.
Yeah. Okay. Now, Ahana, you can ask.
Yes, sir. So I wanted to ask the difference between the Jeans mass and the Chandrasekhar limit.
Okay. Gene's mass is something like if a molecular cloud, that is the nebula, so that is where the stars are being formed. Okay, that's the beginning of the star. So if that molecular cloud has to come together, okay, that is the first step actually. It has to come together and form a globe of gas or a sphere of gas. Okay, it has to collapse. Okay, so that collapse will happen only if it has the gene's mass. Okay, otherwise it cannot collapse. That is the first thing. So the collapse and the protostar formation only happen if it has gene mass. Now, about the Chandrasekhar limit, that is also another mass, that is 1.4 times the solar mass. So, if a white dwarf star has to be stable, okay, if a white dwarf star want to exist like that, exist as a white dwarf, then its mass should be below the Chandrasekhar limit, okay, and if it is above the Chandrasekhar limit, it becomes something like a neutron star. Okay, so that is actually defined by it.
Yes.
Yeah. Now, Trisha Vishakarma. Yeah.
Yes, sir.
Yeah.
So my doubt is, how molecular clouds are formed?
Yeah, molecular clouds are actually formed, especially it is formed from another star actually. You should initially there was only, after the Big Bang there was only hydrogen and helium. There is not much molecule. Maybe hydrogen molecules will be there because of the lower temperature. Now other molecules actually formed after the supernova explosions of another star. So whatever you are seeing as nebula right now, the colored pictures and all, the one I showed in the first slide, like the pillars of creation, all those material, what you are seeing, that beautiful material actually come from the death of another supernova or death of another star. Okay, so that is how it works. The remnants of one set of or one death becomes the another set of star. Okay.
Okay, sir.
Yeah.
Thank you, sir.
Now, Vihan Rajput.
My doubt was that what is the difference between a nebula and a planetary nebula?
Yeah, okay. Even though that name is actually kind of nebula is actually the molecular cloud from where the stars are being formed. Okay, so that is the beginning of a star. Okay, and planetary nebula is also a cloud of material. Okay, you can see that it has some similarity because it looks like some colored clouds. So that is why it is called nebula, and it called as a planetary nebula. Okay, so they have connection. They both are called a nebula because it is kind of a cloud of gases. So that is why they are called uh, uh, what is called a nebula. And if you particularly say what is a planetary nebula, it is the end stage of a low mass star. And what is a nebula? That is where the uh, birth of a star happens. Okay, anyway, they have common name, that is nebula, because both are something looks like a cloud of atoms and molecules. Okay, basically gas clouds. Now, Akshansh Singh.
Sir, I want to ask that what is the meaning of dispersion due to thermal pressure?
Dispersion due to thermal pressure. So dispersion here means, in that context, the that is some if there is high thermal pressure or high temperature, and due to that high temperature, what you mean by dispersing? So when there is an assembly, or in your assembly or a group meeting is there, we at the final we say that the meeting is dispersed. That means you have to go away, everyone will go to their own place, something like that. If the temperature is so high due to high thermal pressure, this star can disperse. Okay, so the star cannot stay together. That is called the dispersion. Here the meaning of dispersion is different from what we have learned in the first or second classified. Okay, so this is actually, the star is not what to say, it expands, or the star won't form. Okay, the star is getting dispersed. Okay, that is it.
Okay, sir, understood.
Yeah. Sachi Arvind Swarup.
Yes, sir. Am I
Yeah,
audible?
hi. Yeah, audible. Yeah.
Yes, sir. So my doubt was, why do stars with a higher mass have a shorter lifespan?
Yeah. So the and the opposite as well. So the
Yes.
reason is something like so when the star is so massive, the problem is that, for example, have some space here. Okay, so when there is some where I will draw, I don't have enough. Okay, let me draw somewhere over here. Okay, so when the star is so massive, its gravity is also more. Okay, when compared with a small star. So there is a small star and a big star, or that means a massive star and a less massive stars are there. And massive star means more gravity. More gravity means the pressure at the center is so immense when compared with the pressure of this. Okay, because the entire gravity is actually acting towards the center. That means here the center has more pressure. Here this for a normal star or a smaller star, the center pressure will be less. So what is the problem? If the center pressure is more, here is where the nuclear fusion happening, that reaction is happening, that energy generation is happening. So when there is high pressure, the energy generation is also faster. Okay, here the energy generation will be much slower since the pressure is less or the gravity is less. So for high mass stars, the gravity is more, so at the center the energy generation is so fast. So since the energy generation is so fast, means that much fast the fuel will completely we will run out of fuel. Okay, so that is the problem. It is something like this. It's not a correct analogy. Anyway, you can imagine, suppose you have a bike and you have a car, which burns fuel more for the same kilometer? Obviously it is car, because the car has to carry the entire mass of itself, something like that. So anyway, it is not the correct analogy, but you can remember it using that. It is not an analogy, it is something to use to remember that. But here this is what is happening. The more massive the star is, then at the core the energy generation is so fast, so the fuel will be burning at a faster pace, so that it will die soon.
Okay. And how does a supernova turn into a black hole?
So supernova is the explosion, but what remains is that becomes the black hole. So after the supernova, what remains? That is basically a neutron star will be there. Okay, a star which is made up of completely neutrons. Okay, and that neutron star, if the mass of that neutron star is more than some 3 solar mass, okay, so 3 times the sun. If that neutron star has a mass of more than 3 times the sun, then it even collapse. Okay, so already its size is some 20 to 30 kilometer only. Again it collapses and forms the neutron star. So again, that depends on the mass. The neutron star is becoming the black hole.
Okay. And I didn't get the red dwarf star.
A red dwarf I haven't mentioned. That may be brown dwarf. I haven't mentioned the red dwarf anywhere. Yeah.
Okay. Thank you, sir.
Yeah. Okay, then Ayan Singh, you can.
Yes, sir. Good evening, sir.
Good evening.
So I'm having two doubts that in the presentation you told that at the means in the birth of the universe there was only two compartments like hydrogen and helium. So how does the star makes the iron, carbon, and nickel in the that cycle?
Yeah, they are making it. Yeah, that's your question already consists of the answer. So initially there is only hydrogen and helium, but that hydrogen, anyway, mostly hydrogen, that hydrogen will convert into helium during that process. Okay.
Yes, sir.
Then that helium is being converted into carbon and oxygen. That is becoming another. So all the remaining elements that you are seeing, or the materials or matter, is being prepared inside the star. So that is how we have all these things.
Okay, sir. And secondly, if the neutron stars are having a very strong gravitational force and pull, and also very strong magnetic field, so how doesn't it collapse in it? Because it is having a very strong magnetic field.
Strong magnetic field has nothing to do with the collapse actually. So if that is something has to do with the gravity. So anyway, that magnetic field is not opposing the gravity. Okay. So in the case of that neutron star, if its mass is more than that 30 solar mass, then it can collapse. There is nothing to do with the magnetic field actually.
Okay, sir. And sir, the neutron stars are made up of only neutrons, or it is having the electrons,
No. There
atoms
is no
in it?
electron. No electron. It is actually completely made of neutrons.
Okay, sir. Thank you, sir.
Okay. So Vaishnavi Maurya.
Good evening, sir.
Good evening.
Sir, I want to ask that what is the minimum mass for an object to be classified as a brown dwarf?
Its mass will be less than 80 times the mass of Jupiter, or 0.08 times the mass of Sun. Okay.
Okay, sir. And sir, I want to ask that will you give questions from these slides from between, or we have to learn from the PDF provided by Adumitra?
You will get the copies of these slides. Okay, so you can learn from this. Anyway, whatever I discussed, there won't be questions from the entire slide. Okay, because entire slide in the sense that there are many topics which is actually above your level right now. So there won't be questions from that. But there will be questions from what I have discussed here. Okay, what I have taught you.
Okay, sir.
Okay, but you can use these slides as a reference. Okay.
Okay, sir.
Yeah.
And sir, what is the qualifying marks?
That I don't know. You can contact Dimitra. Okay.
Okay, sir. Thank you, sir.
Okay. Now Arnav's Galaxy Note 9.
Yeah, hello, sir.
Hello. Hi.
Yeah, good evening, sir.
Good
I
evening.
just, yeah. So as you said earlier that the stellar nebulas, which are the nurseries basically for stars, so they are formed by dying stars, right?
Yes.
So then they should be planetary nebulas, right?
They can be remnants of planetary nebula, or maybe some supernova remnants. So it will be a mix of all these things.
Okay, so
It
like
need not be a single nebula as well. Okay. It comes from many different nebulas actually.
so like a so like a nebula is not the final stage of a star.
We cannot say that it is a final stage. It's something like a cycle. So from a supernova explosion or the planetary nebula, there will be some material will be ejected to the space. It will stay there, and from that again another generation of star will be born. So we say that the first generation, after the first generation, every star, the second generation stars are all formed from the remnants of the past stars.
Okay, so like the cycle goes on and the
Yeah.
universe is expanding infinitively.
Yes, exactly.
Okay, and one more thing, sir. As you said about protostars, sorry, not protostars, neutron stars, they rotate as well, but they do not rotate on a fixed axis, right?
They are actually rotating on a fixed axis.
But they rotate in a weird manner, as I have seen.
Yeah, they are rotating in a weird manner, but its axis is almost fixed. I think it's the
Yeah, like, its axis is like a circle, basically. The point.
it's not. It's basically rotation. It is on a fixed axis itself, and because of that rotation, that light pulse comes in certain direction. The light from that will come. So it makes something like a circle.
Okay, but yeah, one more thing. Are they luminous, like highly luminous?
That neutron stars are not that luminous, I think, or we are actually detecting them because of that light coming from it. So luminous in the sense it is not completely luminous. Actually, it should be luminous because of high temperature. But the most important thing that we notice in a neutron star is the jet of light coming from the two sides, okay, or
The
two
radiation.
axes. Yeah, the radiation coming. Yes, exactly.
Okay, and one more thing about black holes. I don't the picture that you showed us about the black holes. So you said that it is so dense that it doesn't allow light to pass through it, right?
Yeah.
So it's basically black,
Yeah.
as we know. So
Yeah.
because of that, the picture that was taken, was it because of the technology or was it because the light could not reach us?
Yeah, it is not just the it is not because of the anyway technology had some limitation, that is anyway, but even though even the technology get advanced, the problem is that we cannot see beyond the center because there is no light is coming. Even this in this picture, what you are seeing like a donut or something like that
No,
shape is actually the accretion part of the outside part of the black hole.
yeah, the outside part. I know the actual black hole is inside, and the
Yes,
outside part is
exactly.
all the matter that was left out.
Yeah.
Yeah, but is that because as we know, the outside part is actually also blur, right? So is that because of the black hole or because of the technology?
That is because of the technology for sure. That is the
Okay.
maximum. That is actually we use the radio
Yeah,
telescope.
I have heard of this photo. It's the most clear photo of a black hole, right?
Yes, exactly.
Okay. Thank you, sir.
Okay. See you. Now, Sumeda, sir. Sumeda, you can ask.
Hello, sir. Good evening.
Yeah. Hi, good evening.
Sir, I have two doubts. My first question is, what are pulsars?
Okay. Just this. Yeah. Pulsars are actually pulsating stars. That is the meaning of that. So when a neutron star is formed, okay, so the neutron star is actually not stable. Okay, stable in the sense that it is also rotating. Okay, but during that rotation, even along with that rotation, there is light is coming from the star. Okay, so a lot of light is coming, radiation is coming in both direction, not just one direction, in both direction, that is light is coming. Now imagine that it is rotating again like this. So when it rotates, whenever this light is coming towards earth, we see them. When it is goes around, we won't see. Again it comes back, again comes back. It is something like a lighthouse. So it will keeps on pulsating. When the light is towards us, we see. When it is go away from us, we won't see. Again it come back, we see. So something like a lighthouse, and that is why it is, we feel it as like pulsating, and that is called the pulsating star, or in short, pulsars.
Like how it is generating the light or the radiation beams which are going through? Like how it is generating it?
I don't know the exact mechanism of that, because it should be a very high temperature thing and heavy magnetic field is there. That may be the cause, but I don't know the exact mechanism why it is happening.
Maybe because I'm just suggesting that maybe it's moving about its axis at a very high speed, so like that it's generating such a uh, it's not negligible, the light is not negligible, it's so much bright, that's why it's just
Maybe,
generating.
maybe, yeah,
Maybe.
maybe, yeah.
And my second question is, what is solar mass?
Okay, solar mass means, so whenever the problem is that, or one convenience is that, if you want to say the mass of something, something like something has a mass of 3 times the solar mass, something like three. So instead of saying the entire mass directly as a single number, it is always easier to compare its mass with the sun's mass. So we are saying that when an object has 3 solar mass, okay, the meaning is that its mass is 3 times the mass of sun. Okay.
So solar means only the sun, not
Yeah,
all.
yeah, only the sun. So we are comparing it. It is for easiness we are saying. So we say that my height is 3 times the height of my kid. I can say like that. Okay, so I have 3 times the size of my kid is my height. So it is actually comparing. Similarly, we can compare the mass of anything with the solar mass or Jupiter mass, something like that. Okay, so that is just a comparison. So whenever you see that something has 8 solar mass, okay, a weight of a star is 8 solar mass, meaning it is 8 times the mass of sun. So I don't remember the exact value. We something around 10 raised to 36 or something like that. I forgot. Anyway, we have seen it yesterday. So that much times the mass we have to put it here. Then only it becomes in kilogram. So instead of saying it in kilogram, that big number, we can just simply say that it has a mass 8 times that of sun. That's
Then we say that it's 8 solar masses.
yes, exactly.
Okay, sir. Thank you, sir.
So now, Dia MP, you may just a second. What happened?
Yes, sir. So you said that in one of your slides that above the helium, which is not burning, there is burning hydrogen. Then why can't that hydrogen fuse and become helium?
Hydrogen burning means, okay, I'm sorry that I should have been properly written like that. So when I am saying hydrogen burning, that hydrogen is also converting into helium. Okay, your doubt is correct actually. It is actually converting into helium. Okay. Now, Krishai Sala.
Yes, sir. I have 3 questions.
Yeah, okay.
Sir, one is that you talked about the white hole. So, which is more massive, white hole or the black hole?
White holes
Not
are
white
just
hole,
a
sorry, the white dwarf or the black dwarf?
white dwarf or the brown dwarf. The white dwarf are the massive one.
No, with a black dwarf. You talked about that after trillions of years it would be formed.
Yeah, okay. Then even though that black dwarf will be massive.
Black,
The comparison is, can you repeat the question? You are comparing between?
black dwarf and white dwarf.
Okay, then both of them will have almost the similar mass. Okay, because the same thing is becoming the black dwarf. So the mass should be comparable.
And second question is that in the black hole there is the accretion disk.
Yes.
Is it then what is it containing the accretion disk?
That consists of many material like the clouds, the molecular clouds material will be there. There may be material from the stars, something like a plasma, hydrogen, etc. that is being orbiting around the that black hole. Okay, so you know that disk already. So that is the material consist of. All the stellar material, mostly hydrogen.
And my final question is that in just like in neutron stars, there is the GRB, the gamma ray burst. Then, like sometimes in black holes, also this type of from the singularity, a beam is created. What is that?
They are called quasars actually.
So, what are they?
There also when okay, when the black hole accrete more and more mass, and when it is something like we can say that when it is full, so that mass being converted into very high energy beams actually. So due to that, that high energy beams are called the quasars. High energy beams that is emitted by the black hole is called the quasars. Usually supermassive black holes do that, and then around that galaxy forms and things happens.
Okay, thank you, sir.
Okay. Now, Manasvi, you can ask. Yeah.
Sir, I have 3 doubts.
Oh, everybody has 3 doubts. Why there is no 2? Okay. Anyway, ask. Shoot your questions.
So, first one is what are disk formation?
What are disk formation? Okay. So disk formation means when a star forms, okay, so much material is coming into it and it is actually forming like a disk around that star. Okay, so after the birth of the star, this disk where the new planets actually forming. Okay, so they are called also this has a name called a protoplanetary disk. Okay, so that disk is a material which is actually orbiting around the star during the formation of the star, and even after the formation of the star, eventually that becomes the planets. Okay, next question. Hello, Nasvi, are you there? Cannot hear you. Hello. Okay. So now Advika Singh.
Yes, sir. I have two doubts.
Yeah.
First is that when are we going to get these PPTs that we are doing in these sessions?
Can you repeat?
I am asking that when we are going to get these PPTs that we are doing in these sessions.
I think maybe after tomorrow also there is one more class. Okay. That's your last class. After that last class, maybe Saturday you will receive it.
And sir,
On or before Saturday you will get it.
Okay, sir. Thank you, sir. And the second doubt is that in our reference book, there was a question that was, what is Hubble's law? And the answer that was given is the theory that the universe is contracting.
Okay, you do one thing. I think that if I think as you said that question, the answer is wrong. Maybe some type error or something like that. Anyway, what you can do, you just take a picture of that and just send to EduMitra. Okay.
Okay, sir.
Then I will receive it from there and I give you the corrections will be written back to you. Okay.
Okay, sir.
Now once again, Chakri.
So that time I was having more doubts. That time you muted me. So, sir, another one is, what if even two neutron stars collide?
Yeah, when two neutron star collides, again it becomes a black hole.
Sir, even I have another doubt, sir. Would say two again could a black hole collapse on itself?
No, black hole, that is the maximum.
Oh, okay, sir.
Okay, so there is another question in the chat from Manu, that is, what are the internal process that keeps the star alive? That's only one process, that is the nuclear fusion. It may be the fusion of hydrogen to helium or helium to carbon or carbon to nitrogen. So whatever it is, that nuclear fusion is the energy source of star, and that is what is keeping the star alive. So now the time is 7:10, so I am stopping it here. And this will be my last class, and tomorrow's topic will be handled by another faculty from EduMitra. So I'm wishing you all the best for your future exam and all. Okay.